Hello friends, welcome back to my channel. In today's video, I'm going to discuss Fick's first law of molecular diffusion through a binary liquid solution. I have already discussed Fick's first law of molecular diffusion, then how it is applied for diffusion through binary gas mixtures. I have already shared my videos on these two topics. I'm giving links to those videos in the description section. Please watch those videos. For today, let us talk about molecular diffusion, and specifically let us talk about Fick's first law for molecular diffusion in liquids. How to apply the law, what will be the mathematical statement for the law if it is applied for molecular diffusion in liquids. So as I said, we will be talking about molecular diffusion in binary liquid solutions. What are binary liquid solutions? These are those liquid solutions which have only two components in them. We are going to talk about such binary liquid solutions. Now to begin with, let us understand this fact. What is the fact? As compared to gases, molecular diffusion in liquids is difficult to understand. Or you can say it is difficult to predict molecular diffusion in liquids as if you compare that with gases. In gases, you can accurately predict how molecular diffusion occurs. But for liquids, it is difficult to predict the diffusion process with accuracy. What is the reason for that? The reason is no sound theory is available for liquids that can describe their structure. No sound theory is available that describes structure of liquids. For gases, you have the kinetic theory. You have the kinetic theory of gases. So whatever equations we have for molecular diffusion in gases, all those equations, they are based on this kinetic theory of gases. And that is why their results are more accurate. Their results are more accurate. But for liquids, you don't have any such theory. And that's why whatever equations that we have for gases, they will give comparatively less accurate results. The only reason is you don't have a sound theory that can describe structure of liquids. For molecular diffusion, as I said, we are going to discuss molecular diffusion in binary liquid solutions. So we have two components, liquid A and liquid B. And let us talk about molecular diffusion of liquid A in liquid B. So for molecular diffusion of liquid A in liquid B, what is the case? Diffusion coefficient. Diffusion coefficient of A in B, that is DAB, and the total concentration. These two quantities. Which two quantities? The diffusion coefficient, that is DAB, and the total concentration, that is C, total molar concentration. These two quantities, they appreciably change along the diffusion path. They appreciably vary along the diffusion path. So as you move from one end of the diffusion path to the other, these two quantities change, and the change is appreciable. You will have to consider that change. This is the case for diffusion through liquids. But for gases, these two quantities, that is the diffusion coefficient and the total concentration, the variation in them is negligible. For gases, their variation is negligible and they are considered to be constant. While our analysis for molecular diffusion in gases, we had considered these two quantities to be constant. You can just go and watch those videos. You'll understand the concept. But here for liquids, they change appreciably along the diffusion path. So we need to have we need to have a solution for this. How to tackle this problem? So what we will do, or what is done in this case, if these two are changing appreciably, we use an average of values of DA, B, and C at the two ends of the diffusion path. So I'm going to show that schematically. So you have two ends of the diffusion path. At these two ends, you have different values for DAB and C. So what we do, we take average of those two values. You take average of DAB at the two ends, you take average of total concentration at the two ends, and consider this average values to be constant. So this is how uh, we are tackling the problem of variation of DAB and C uh, for diffusion in liquids. So an average values of DAB and C at the two ends of the diffusion path, they are used in the analysis. Uh, as I said earlier, a little is known about diffusion coefficient, true values of diffusion coefficients in liquids. You can get accurate values through experiments. There are equations. I'm going to discuss that in one of my videos in future. Whatever equations you have for predicting diffusion coefficients in liquids, they give less accurate results. The reason is little is known about diffusion coefficients in liquids. So for that, what is done? Their best known values are used. Whatever values are available in literature, whatever experimental or you carry out, you may perform some experiments for diffusion, molecular diffusion of liquids, molecular diffusion in liquids, and you may get your own values of DAB. So experimental values, as if you compare them with the values that you get by using equations, experimental values will be more accurate. Okay, so the point is if you have to use those, if you have to use values of diffusion coefficients in liquids, you use those values that are well established, best known values of diffusion coefficients you can use. Okay, so let us understand this with the simple schematic diagram. So you have one diffusion plane, one plane, that is z is equal to 0, and you have the other plane z is equal to z. And if diffusion is taking place from this plane, from the plane z is equal to 0 to the plane z is equal to z, in reality what is happening, as you move from the plane z is equal to 0 to z is equal to z, DAB and C, they are going to change appreciably. Their change is appreciable. So what is done? Okay, the diffusion is taking place. If component A is diffusing, then at the plane Z is equal to 0, if its concentration is Ca1, and at the plane Z is equal to Z, if its concentration is Ca2, then Ca1 is greater than Ca2. That's why the diffusion is taking place in the shown direction. Okay, so at the plane Z is equal to 0, you have one value of DAB1 and you have one value of total concentration. Similarly, you have at the other plane, that is at Z is equal to Z plane, you have one value of the diffusion coefficient, that is DAB2, and one value for concentration, that is Ca2. So the point is DAB and C, their values are different at the two planes. You have a different value at, you have different values at z is equal to 0, and you have some different values at z is equal to z. So what is the point? The point is we have to use average of DAB1 should be the best known value at these conditions, and DAB2 should also be the best known value at these conditions, and you take average of these two and use it in the analysis. Similarly, you take average of C1 and C2 and use that average in the calculation. In other words, average values, you can consider them to be constant, and when we do integration in the analysis, you can take those values as constants. You can consider those values as constants and you can take them out of the integral. You're going to learn that. Okay, so DAB1 average values, they are considered to be constant. Now, having understood how to deal with variation in DAB and C, now let us move ahead. Now let us talk about the main thing. What is that? How to give Fick's first law of molecular diffusion for liquids in binary liquid solutions. ठीक है? The mathematical statement for Fick's first law I have already discussed in my previous video, in my videos on this particular topic. I have given links to those videos in the description section. You please watch those videos. So let us take the statement from there. The mathematical statement for Fick's first law of molecular diffusion. We are considering for diffusion in a binary mixture of components A and B. You have this statement: JA is equal to minus DAB dCA by dZ. Fick's first law states that molar flux is directly proportional to concentration gradient, and if you remove the proportionality, you need to have a proportionality constant, and you have this proportionality constant DAB, which is the diffusivity of A in B or diffusion coefficient of A in B. The negative sign in this equation indicates that diffusion is taking place from a place of high concentration to a place of low concentration. ठीक है? Ja is molar flux of A relative to molar velocity of B. J type of flux. There is a J type of flux. Again, you have two types of fluxes, J type flux and N type flux. I have discussed that in the videos, for which you have link in the description section. So Ja is the molar flux of A relative to molar velocity of B. DAB is the diffusion coefficient of A in B, which is the proportionality constant in Fick's first law. And dCA by dZ is concentration gradient of A in the Z direction. So how concentration of A, molar concentration of A, changes in Z direction, this is given by this particular term, dCA by dZ. So dCA by dZ is concentration gradient of A in Z direction. Likewise, you may have concentration gradient in other two directions, dCA by dx, dCA by dy, but here we have neglected that in those concentration gradients. We have just considered concentration gradient in Z direction. Okay, that's why you have a total derivative. If there was appreciable diffusion in the remaining two directions, you must use a partial derivative over here. Okay, so a total derivative over here indicates that diffusion in other two directions is neglected. Okay, now mole fraction of component A is, how do you get mole fraction for component A? This is Ca upon C, that is molar concentration of A divided by total molar concentration. So how is this going to, how are you going to understand? Molar concentration of A will be moles of A per unit volume, per unit total volume, and total concentration will be total moles per unit total volume. Okay, so Ca upon C is nothing but moles of A per unit volume divided by total moles per unit volume. So this V and V gets cancelled, and you are left with Na upon A, Na upon N, that is moles of A divided by total moles, which is nothing but mole fraction of A. And we are going to denote mole fraction of any component in liquid solution by X. So small xa over here stands for mole fraction of A in the liquid solution. Okay, so mole fraction of A, this is Ca upon C, molar concentration of A divided by total molar concentration. How do you describe molar concentration? Molar concentration is moles, over here I have explained, this is moles per unit volume. Moles of A per unit volume is molar concentration of A, moles, total moles per unit volume is total molar concentration. Okay, so the point is mole fraction of A can be described in this way: X is equal to Ca upon C. So if you rearrange this equation, let me first erase it so that I hope you have understood it. If you have any doubts, I have already told you. You please mention that in the comment section. Okay. So from this equation I have written this equation, Ca will be equal to Xa into C. If you differentiate on both the sides, it will be dCA is equal to C into dXA. You please note over here, total concentration C, it is constant. It is considered to be constant, and it is coming out of the derivative. Okay. So if it is constant, it will come out of the derivative, and you just have to take derivative of Xa. So the point is dCA will be equal to C into dXA. Okay. Ca is molar concentration of A, and C is the total concentration. I have already talked about it. Okay. Now, and C is the total concentration, and C is constant. That's why you get this equation, dCA is equal to C into dXA. There is only differentiation of Xa because that is changing. Okay. So this is explanation for this statement. This is explanation for this statement. Now we are going to use it for liquids. Let us understand how to do that. Okay. So from the previous discussion, we have this equation. Now, so you had the law on my previous slide. I had written this, JA is equal to minus DAB into dCA by dx. Sorry, dCA by dz. So you have this equation on the previous slide, and then at the end of previous slide we had got this relation, dCA is equal to C into dxa. C into dx. Okay. So how this equation is obtained? So in this equation, which is the mathematical statement for Fick's first law, we are replacing dCA with C into dxa, and C is constant, as I told you. It is, and that's why it is out of the derivative. So you get this equation, JA is equal to minus DABC dxa by dz. Okay, so Fick's first law, now it is written in this way. Okay, so I hope this is clear to you. So we have in the mathematical statement for Fick's first law of molecular diffusion in binary mixtures. It could be gas mixture or liquid solution. Okay, for that you have the equation, J is equal to minus DAB into dCA by dz, and then Xa is Ca upon C. Therefore dCA is C into dxa, and in this equation we have used that. So you get this equation. I hope this is clear to you. If this equation is not clear to you, you just go back to our previous discussion, you'll understand that. So Ja is equal to minus DABC into dxa by dz. Now the total concentration, it is difficult to measure. So if you have liquid solution and if you want to measure total concentration at any point, it is difficult to measure. Now this is not the case only with it is also true for gas mixtures. Total concentration, you have to, if you want to know what is total concentration at a point in a solution, you will have to go to that point, and then you will have to measure the total concentration. So it is difficult to measure. You will have to use sophisticated instruments for them, and you have to be very careful while measuring the total concentration. So the point is, the general point is, total concentration C, it is difficult to measure. Hence, it is expressed in terms of measurable quantities. So if you express C in terms of measurable quantities, and that means in terms of those quantities which you can easily measure. So there is no need of measuring total concentration. You measure those quantities which you can easily measure, and if you have equation for C in terms of those quantities, you can use that. Okay, so hence that's why we are saying it is expressed in terms of measurable quantities. Now let us learn how this is done, how to express C in terms of measurable quantities. Okay, so C is defined as, how is C defined? C is nothing but total moles of a substance per unit volume. That is, C is equal to N upon V, total moles divided by total volume. N represents total moles, V represent the volume. Okay, but total moles of a substance, how do you calculate? The total moles of a substance is the ratio of its mass to its molecular weight. So for example, this will be N, total moles is equal to total mass divided by molecular weight. Over here I have used average molecular weight, because when you have solutions, when you have mixtures, there will be the mixture or the solution will have an average molecular weight. So that's why in finding total moles, we need to use average molecular weight. You must be knowing how to calculate average molecular weight of a mixture or a solution. If you want me to make a video on that, you please mention that in the comment section. I'll make a separate video on that. For time being, you please note, for solutions or mixtures, we need to use average molecular weight. So total moles will be total mass divided by average molecular weight. So M represents mass and MW average represents the average molecular weight. So in this case, it will, since we are discussing it for liquids, this will be average molecular weight of the liquid solution. Okay. So the point is, we started with the general statement for Fick's first law of molecular diffusion, and now we are moving ahead so that we can apply it to liquids. Okay. So we have transformed the general statement of Fick's first law for molecular diffusion in a different form. Now you can see, you instead of how molar concentration changes along the direction, we have how mole fraction is changing along the direction. And then, since total concentration, that is C, it is difficult to measure, we are going to express that in terms of measurable quantities. So for that we have used definition for C, total moles per divided by total volume. Total moles is total mass divided by average molecular weight. Why average molecular weight? I have already talked about it. Okay, so let us move ahead. From our previous discussion, you have this equation for C. Okay, so C, I'll just write it once again. So on previous slide you had this equation, N upon average molecular weight. Sorry, M upon, just a minute, just a minute. On the previous slide you have this equation. We had this equation for N. What was that equation? Total mass divided by average molecular weight. So over here what is done, I have used equation for N in the equation for C. So in place of N I have written M upon MW average. So C total concentration is equal to M upon MW average divided by V. If so we are going to use it in the mathematical expression. So we are, whatever we get the final equation for C, we are going to use that in the mathematical expression for Fick's first law. Now for time being, let us understand this. So we get this equation. In the next step I have rearranged it. C is equal to M upon V divided by M average, just rearrangement. And what is M upon V? Mass upon total volume. The mass per unit volume is nothing but density of the solution. So density of the solution. So at the end you get C is equal to rho upon MW average. That means total concentration now is expressed in terms of density of the solution and average molecular weight of the solution. Both the quantities, density, it is, you can measure it easily. and average molecular weight. If you know the composition, you can find out the average molecular weight of the solution. Okay, so we have expressed C in terms of density and average molecular weight of the solution. And now let us follow this statement. What is the statement? Using this in the mathematical expression for Fick's first law. Again, you remember what was the expression? Expression was JA is equal to minus DAB. JA is equal to minus DAB into C into dxa by dz. Now in place of C, we are going to use this expression. So you have JA is equal to minus DAB in place of C. Now I'm writing this term rho upon MW average. I have expressed C in terms of rho upon MW average into dxa by dz. Okay, so in this way we converted the general statement for Fick's first law for molecular diffusion to a form that can be used for liquids. So for liquids, you can use this form of Fick's first law of molecular diffusion. JA is equal to minus DAB into rho upon MW average dxa by dz. Again, for liquids, these two quantities, they are going to change. So when we do the analysis, when we discuss cases, we are going to discuss two cases. One is liquid A diffusing in stagnant liquid B, and the second case is equimolar counter diffusion of liquid A and liquid B. I'll be posting separate videos on those two topics. You please you watch those videos when I post them. Okay, there I will tell you how to deal with these two terms, because for liquids these two terms are going to change along the diffusion path, and as I discussed it previously, we are going to use average values of these two quantities. So how to use them, how to do the integration, how to get equations for rate of diffusion in those two special cases, we will understand in our future discussions. I hope you have understood what I have discussed today. I hope you have understood how to modify the mathematical statement for Fick's first law and make it suitable for use with molecular diffusion in liquids. I hope you have understood the concept. If you have any doubts, you please mention in the comment section. Please subscribe to my channel. Please hit the bell icon so that you'll get notified as soon as I upload any new video. And I'm at regular intervals, I'm going to upload videos on various aspects of chemical engineering. Now I have started doing it for mass transfer operations. Simultaneously, I will be doing for some other subjects, process calculations, some basic fundamental concepts of chemical engineering. So you please stay with me. You subscribe to the channel. For time being, thank you for being with me. Hope to see you soon. Bye. Have a nice day.